Welcome back, Physics 30. This will be the second part of the Part 2 video. So we just looked at defining what volts are, what electric potential differences. So now we'll look at a few questions involving that, and that'll be very close to take us to the end. So what amount of energy, and of course energy is equivalent to work done, does a kettle use to boil water if it has 8.0 times 10 to the 2 coulombs of charge passing through it with a potential difference of 120 volts? So of course potential difference, layman's terms, that's voltage, 120 V. My charge is 8.0 times 10 to the 2 coulombs, and I'm looking for work done. So of course here's my relationship, V is equal to W over Q. If I rearrange it for W by multiplying each side by Q, I get that. Now it would be beneficial to, instead of referring to electric potential difference as volts, convert it back to joules per coulomb, because the units will work out nice. 120 joules per coulomb times 8.0 times 10 to the 2 coulombs. Coulombs cancel, and I'm left with joules as my final unit for work. 96,000 joules. B, what is the potential difference across a refrigerator that if 75 coulombs of charge transfers 9.0 times 10 to the 3 joules of energy to the compressor unit? So why don't you set up the variables, what we know, what we're looking for, and see if you can work that equation. So maybe pause the video right now and see if you can work through that one. Okay, if you had a chance to work through that, we have volts is what we're looking for, potential difference. The charge is 75 coulombs, work done 9.0 times 10 to the 3 joules. So of course we have V is equal to W over Q. We have W, we have Q, so I'll get 120 joules per coulomb, or 120 volts. Okay, this next one is going to use a few equations. As you can see, an electric baseboard heater draws a current of 6.0 amps. That is current. So the tough thing about this is just remembering what do each of these units represent in terms of a variable. So current is in amps, 6.0, and has a potential difference of 240 volts. So big V, 240. For how long must it remain on? So how long, that's a time we're looking for, if we're using 2.2 times 10 to the 5 joules of electric potential energy. So here we have work also, and we're asked to find time. Now if we take a look at what we could possibly do here, we know V, we know W, so if we know V and W, that will allow us to figure out what Q is. So rearrange this equation, just interchange Q and V. Once I know what Q is, I'm given current, and yes, current is I, Q I will have figured out, so that will just leave T left over. So there you have it. That's the rationale as to how we will figure out this question. So V is equal to W over Q, or interchange the Q and the V. Q is equal to W over V. As you noticed, I put V in terms of joules per coulomb so that the units cancel out nicely. Joules and joules cancel. Coulombs flips up to the top, 916.6 coulombs. Similarly here, to solve for T, interchange the I and the T. So T is Q over I, my 916.6 coulombs over my 6.0, that coulombs per second, and as you can see there, amps is also coulombs per second, so I could put that as a unit there. Therefore coulombs will cancel, left with seconds, 153 seconds. And of course here I have 2 sig figs everywhere, so I rounded that off to 150. Okay, last one on this page. A flash of lightning transfers 1.5 times 10 to the 9 joules of energy through a potential difference of 5.0 times 10 to the 7 volts between cloud and the ground. Calculate the quantity of charge. So W, V, Q, of course there's my relationship there. V is equal to W over Q. Looking for Q, so just interchange that with V, and the equation becomes Q is equal to W over V. V I changed to joules per coulomb, so you can see the units cancel out nice, and I get 30 coulombs. 2 sig figs everywhere, so I put a bar over that 0 to indicate that that 0 is in fact significant. Okay, have a few more here, and a couple of other things to talk about in terms of circuits, and then the vocab comes here in a bit. Alright, so we just did this question here. Let's look at this one. Calculate the energy, and of course energy is work done on it, stored in a 9-volt battery that can deliver a continuous current of 5 milliamps for 2.0 times 10 to the 3 seconds. Now, milliamps, we have to change that to amps. Quite easily done. 1,000 milliamps in an amp. Make sure you have that down. Just like 1,000 meters in a 1,000 millimeters in a meter stick. So we know V, we know I, we know T. We're asked to calculate W. So as you can see here, this is how we will do it. W we don't know, V we do know, Q, hey, we don't know, but we do know what the current is. If we know what the current is, and if we know what the time is, we can figure out Q. Then once you know Q, we can then figure out the work. So interchanging this for W, multiply each side by T, I get Q is equal to I times T. 0.0050 times 2.0 times 10 to the 3, that gives me 10 coulombs. So I rearrange this to isolate W, multiply each side by Q, so W is equal to V times Q, 9 times 10, 90 joules. And of course 2 sig figs everywhere, so I put the bar over the 0 to indicate that that 0 is significant. Now, last question, I believe. If a charge of 0.30 coulombs moves from one point to another in a conductor and releases 5.4 joules of energy, what is the potential difference? So I'm looking for V, I know W, I know Q, so here's the relationship we can use there, of course. V is equal to W over Q, 5.4 joules divided by 0.30 coulombs, 18 joules per coulomb, or 18 volts. So there we have it again. We can figure out electric potential difference. Other useful equations, combinations of equations. So V is equal to W over Q. Work, of course, is force times displacement, so we could make the equation look like that if we needed to. Q, as we saw up here, Q is equal to I times T. So we could leave it like that, or we could have work over IT. So in some of these questions in which we had to use two equations, we could technically just use one if we wanted to substitute different variables in there and rearrange them differently. Okay, the last part of this now, we'll look at schematic diagrams leading up into the next booklet. What is the purpose of a schematic diagram? Easy way of representing the components of a circuit and how they are connected. And describe how a battery causes current to flow. It has to do with that idea of one region being or having an electron surplus, one region having an electron deficit, and those electrons would be forced to be repelled from that sufficient area to the deficit area, from negative pole to positive pole. So there's a difference in potential between the poles. Okay, that means one side is a surplus, one side is a deficit of electrons. When the circuit is connected, the difference in potential causes electrons to flow in the wire from a high potential to a low potential. And as those electrons are going from that region of high potential to low potential, they release energy. So you have to think of it as these electrons have energy. As they go through the circuit, they release the energy to do some work on a device such as a light bulb or something else. So lastly here, the instruments used to measure voltages or current. A voltmeter is something that measures electric potential difference, or in layman's terms, voltage. So we're looking at the energy per charge, or the energy lost per charge as the electrons go through a device. So if we think about a schematic diagram, so this smaller line, bigger line, the smaller line usually indicates the negative pole of a battery. The larger line indicates the positive pole of the battery. Going through the circuit, this here is the symbol used for a light bulb, and then back to here, and your duotang, there's one page that lists all of these symbols. So if we wanted to measure the voltage or the potential difference across the light bulb, we have to determine, okay, what was the energy before, what was the energy after. That'll give us an idea of how much energy the electrons gave off in lighting the light bulb. So we say that we hook this voltmeter up in parallel to, so you can see it's parallel to the light bulb, to measure the voltage before and after to see that difference in electric potential. Okay, I think we're running out of time here, folks, so we'll do one more video. We'll start off with ammeter, look at how those are hooked up, and then we'll look at the vocab there and finish it off. So we'll see you